Okay, I appreciate the short introduction. I guess you probably were expecting Lars, but Lars can't make it, so I will do the replacement part in this
No problem,
particular
no
case.
problem. You're more than welcome. You are no more than welcome. Yeah.
It's fitting because I'm also the project manager for this AI project and have an IT background, so I think I will do fine. So our topic is going to be AI for ETA prediction, which is what Eric already mentioned, also in the context of supporting operational efficiency and sustainable quality management through AI. So what we will cover, 3 points. I will try to keep it within 15 minutes. So the first thing is we already had the introduction that I'm from HaCon, but there's also some kind of history and context with Siemens Mobility Software. So I might explain who we actually are, how our department is located within Siemens. Then I would give a very brief and not concise overview of certain initiatives that Siemens has in terms of AI, just to give you some overview of where things are heading, even though, in my opinion, based on all of the speakers, I think we already have a very good overview of where things are going. So it's probably going to be fairly short. And the last part is going to be AI freight ETA prediction. I will give a very brief refresher for ETA in case you're not familiar with that topic. I think most of you probably will be familiar, but it's not complicated, don't worry. And then I will segment that into what we are right now working on in our department as part of EORail, which is the project HITA, which uses AI for ETA prediction. And then obviously a very short closing statement, and maybe you have questions. So let's get started. First of all, HaCon is since 2017 part of Siemens. So we are also part of Siemens Mobility Software, which is basically, you have Siemens Mobility, which is a subsidiary of Siemens dealing with mobility solutions, as you can imagine. And Siemens Mobility Software obviously then provides software for those mobility solutions. So there are all kinds of different products in the portfolio, whether it's a train planning system, TPS, which is, has a customer such as DB. For example, it has TPS TrackWorks for planning of the maintenance of the rail network, but also other solutions for timetable construction, live dispatching, optimization, which will be TPS Plan and TPS Live. Then maybe mobility as a service, where you, for example, have Renfe in Spain use it, but also very much used in Germany here as well, which can be like interpreted as a countrywide platform, allowing users to plan, book, and pay for the trips in a single application. It also integrates different transport modes for seamless door-to-door traveling, as well as other parts of the portfolio. I explained the first two in a bit more detail because this is what HaCon provides, what we provide. And Lars and myself are in TPS. So we are dealing with the train planning system. And TPS has a sub segment, which is TPS logistics, which is why we are here, because we are dealing with the freight topics within that Siemens Mobility Software subsidiary, if you will. So, good. Okay, now that we have some kind of organizational overview, how HaCon is embedded in the entire Siemens world, maybe let's have a brief look at what Siemens does in terms of AI. So we can have kind of like an overview of what you are doing, what we are doing as our little part freight segment. This is only relating to industrial applications. This is not comprehensive of all of the things Siemens does. And to be honest, it would probably be quite an effort to identify all of that for the entire company, as it's a large company. So one of the things you probably notice is Gen AI for software engineering, LLM ops, federated learning, agent ops, which is similar to what other speakers already mentioned, where you have generative AI to enhance software engineering right now. But also, if you look at the timeline, because the more out you are on this entire slide, the further it is in the future, you also have this tendency for agentic developments. So agents are, I think, definitely coming. And Siemens also involved in that. Part of this, obviously, is then also trustworthy AI, because if you use agents, they need to be dependable, they need to be trustworthy. You also have to look at legal matters. This also applies to a certain extent for using generative AI for software engineering, because you have to understand that the training data may be, how can I say, you shouldn't replicate it one-to-one, right? There shouldn't be a one-to-one output. This is for legal reasons. So there are all kinds of legal red tape that you have to consider when using this type of technology. And obviously, there can also be other use cases with multi-modal foundation models, so large foundation models that you can use as a starting point. Maybe you can also use it in robotics, physical AI, and etc. So what we do in terms of our own project, we tend to use primarily machine learning and deep learning, which is not the same thing as generative AI, because most of the developments you see here are generative AI. We also do experiment with the transformer infrastructure, which is where all of this is actually coming from. I think it was from a Google paper back then, but just to give you like some kind of context for where we are coming from. Good. I already mentioned the project we work on, and I briefly mentioned Europe's rail. So the project that we use for the AI models to get better ETA predictions in freight is called HETA, which is, to be honest, it's pretty simple. It's HaCon ETA, right? So HETA, and it's part of EU-Rail FP5. If you aren't familiar with A-Rail is a very large European initiative with all kinds of partners all over Europe, which is there to facilitate the transition from road to rail traffic or transportation. And what we are developing is an AI system to make accurate ETA predictions for freight transportation. And in order to do so, we integrate various kinds of data, including tough TSI, but also geolocation. There's going to be weather data. There's going to be some real-time. EDGIS was already mentioned. We're also on that as well. And we use a mixture of different AI techniques, machine learning, deep learning, also a bit of transformer architecture as well, and incorporated in a lean and agile development process. So in case you have been wondering the entire time, what am I talking about when I say ETA? Really simple. ETA is short for estimated time of arrival, right? So you have here a screenshot from the top and tough TSI sector handbook that showcases that pretty well, I think. You basically have a train run. So you have a train that goes through numerous stations. Say you have a train that transports cargo from Hanover to Munich and then from Munich to Verona, for example. So you have three stations essentially, which then makes the entire train run. And then you have a point from where you ask for a prediction of when that train is going to arrive. So this is what an ETA is. It's an estimation of when you think a train is going to arrive in this instance. That means if you have a message point in Munich and you want to know based on all of the data that the model has analyzed, when is that train likely going to arrive on the forecast point, which then in this case would be Verona, then that is what an ETA would be, right? So for example, in this case, it could be that the message was sent at 16:35, the forecast time was 19:25, but the actual real arrival time was 19:45, and the timetable time, so the planned time, was 19:30, right? You have a calculation down there, but this is more for the metric itself to estimate how good an ETA is. There are specific metrics such as Medicube that do that. So then the next question would be, okay, how's that useful? Well, it's pretty useful in terms of increasing operational efficiency, because if you know that the train is going to be late, you can actually make adjustments, right? You can reduce idle time where resources that otherwise could have been used on different tasks, or you could have made adjustments to the route itself. It wouldn't be possible if you don't know when the train is going to arrive. But if you do know, then you can be far more efficient and improve, reduce dead time and lag time essentially. Another thing you can do is, which is also one of the things that we have noticed and built on, which is a tad larger than just ETA predictions, is if you have that type of data that you use to train a model. So you have all kinds of data, and that is basically the foundation for the model training. This data can also be analyzed with data mining and process mining to find issues and patterns that can then be showcased in a more of a real-time environment. I will show a screenshot regarding that in a few slides. And you can use this to optimize your processes over time, because you have a better overview and you can actually identify processes that you may have been unaware of because they were never properly documented. There tends to be a gap between actual processes and what you think the process is, which is process mining. So all of that can be used to create essentially an entire package that has a lot of interesting benefits in the freight sector, I think. So let's talk about our learnings so far. that we have had from this particular HITA project in terms of creating a machine learning model to predict the estimated arrival of a train at a specific forecast point. So you see here a Sankey diagram of a train ID. So you can already guess that we are using tough TSI data in this particular case. And one of the things we have noticed is that the data tends to be incomplete. So you may have missing information, a train run, and missing contextual information for delays. I'm not even talking about inaccurate information, but just incomplete information in this instance. This, of course, makes model training more difficult because the model doesn't see the entire picture. It only sees a part of the picture at any given moment. And this was one of the major challenges that we faced initially already. Then another thing that we have learned, which can also be an issue, and most of them, as you can guess, relate to data. I think some of the speakers already mentioned poor data in, poor data out, poor results out, essentially, is data integration. So if you integrate data from various sources, and it's not just one source, but it's numerous different sources, then all of this data needs to be aligned before it can be used to train a machine learning model. You can't just take all of those different formats in and throw them into the model. It doesn't work like this. So there's a lot of data pre-processing that needs to be done. A lot of the data needs to be harmonized, aligned, etc. And this gets even more complicated if we are not just talking about a similar data format. Say you have numerous operators that use ADGIS or tough TSI, but we are talking about combining both of them with, say, geoinformation data. Then it becomes even more complex to actually prepare the data for processing. Here you also see a part of the front end that was developed for this system that we are developing right now, which can also showcase some of the ADGIS real-time data from different train runs, and you can also use this to a certain extent, which I already mentioned, for analyzing processes and possibly in the future more data mining, where you can visualize certain aspects of the data with a dashboard. Right? So the data can then be used in a dashboard while at the same time also being used for model training. And another thing that we noticed, which also is interesting, especially if you compare freight to passenger. In terms of freight, the complexity of the data tends to be higher. It's more difficult to actually ascertain why a delay happens, because there are so many different factors that can cause the severity of delay, and the delays tend to be larger. So you tend to have more outliers in terms of the length of the delay. In passenger, it's unlikely that you may have a delay of 8 hours or more, but in freight that can happen. And it becomes more difficult to trace back where it comes from. And in order to do so, you actually need a lot of contextual data and information from different sources to make a more accurate prediction. And maybe something to close this in terms of the machine learning models or deep learning models. We experiment with different models. And we noticed that, unsurprisingly, depending on the model setup you use, you get different quality of ETA predictions. If you use a very simple model such as k nearest neighbor, so that would be k9 on the bottom, it tends to perform significantly worse than if you use a transformer, which is also kind of part of deep learning, or if you use an MLP, which so far as we have right now was the best performance that we had. Boost models also perform fairly well. But the point is that the world of machine learning and deep learning, or AI, is rather vast, and there are different types of approaches you can use. And right now, I think we really focus a lot of the transformer architecture and generative AI. But for certain use cases, it may be more appropriate to use a combination of approaches to determine what actually makes sense and what doesn't. So I think this was pretty much what I wanted to share with you. If you have any further questions, you can ask them now, or you can write Lars or myself an email, and we will try to get back to you. Thank you for your time.